Okay, this is the last part of your notes. So there's like the third page. This is just an example, and this example will require more work. You'll have to like make a scatter plot with your calculator. So have your calculator nearby, and you'll probably need to pause the video a lot more for this one. I also tried to listen to some feedback I got from you guys. The pen sounded like it was pretty annoying, which I thought it might have been. My wife actually has made some videos for her classes, and she said that when she plugs in like the Apple earphones into the iPad, then the microphone in the earphones is the one that is used instead of the microphone in the iPad, and she said that works a lot better. So I might use that next time, but right now I'm just going to try scanning my work in pencil and then just using a laser pointer to kind of show you what I'm talking about and how I did certain things. So have your calculator out, and then feel free to pause whenever you need to kind of play around with your calculator. So we're talking about crawling babies here, and we're curious to see if we have a guess that it looks like babies in colder weather aren't as likely to crawl because they're wearing heavier clothes, long sleeve clothes, things like that. So that's what we see in the data, but now we want to see, can we confirm that guess by a hypothesis test? So our null hypothesis here is there is no association between temperature and crawling age. It doesn't matter when the baby's born, they pretty much crawl at the same age. The alternative hypothesis is that there is an association between temperature and crawling age. And we'll use alpha 0.05. So this is a line regression t-test. So our conditions, and here's where you're going to need a calculator. We need to make sure this is nearly linear. So to do that, you're going to need to put all those data values into L1 and L2 and then make a scatter plot. So go to stat plot after you put them in L1 and L2, make it a scatter plot, L1, L2, and then zoom 9 once you graph it, and then it should show up, and you should be able to confirm, yeah, more or less that looks pretty linear. And then the second condition, independence, just making sure that just because one baby crawls at 32 weeks, that doesn't really make a difference on a separate baby crawling at 33 weeks or something like that. It's not like all the parents, there's like some competition to make their baby crawl earlier than anybody else. So pretty safe to assume we're independent here. And like a good, what's the word I'm looking for? A good, it's really escaping me, but making it random would be a good guard against things being dependent. So making it independent, make sure it's random. Okay, equivariance. We need to look at the L1, like the X variable, against the residuals in order to find out, is there some pattern with that scatter plot. So in order to do this, you first need to run the line regression t-test. So you almost have to do like the do section first before you're able to do this, because the calculator needs to first figure out what these residuals are. And a residual, remember, is just how far off the scatter plot points are from the trend line. So is it a positive residual means that you're underestimating, a negative residual means that you're overestimating. And so, you need to run this test first. So you might do that where you just go to line regression t-test, make sure it's L1, L2, and actually I'll write down a couple things here. When you do that, make sure the beta, the null hypothesis, is not equal to 0. It's pretty much always a two-sided test. And everything else, if I remember right, I don't think you need anything else. So once you do that, then it knows what the residuals are. So then you need to make a scatter plot with L1 as the X variable, residuals as the Y variable. And the way you get residuals in that spot on that screen is you need to hit the second key, then find the list button, which is in blue, or like the secondary function, and then scroll down until you find the one called residuals, and just hit enter on that, and then it will plot L1 residuals, and you can hit zoom 9 again to make sure it shows up. Okay, then again, you're just looking to see there's no pattern there. It doesn't look like a parabola. It doesn't look like they start out really close, but then they get really widespread as you move from left to right. So that's what equal variance means. Nearly normal, make a histogram. So stat plot instead of scatter plot, do a histogram with the residuals, not L1, but with the residuals, and make sure that that looks like it's normal. And I had to play around with it a little bit because it looked not very interesting at first, but if you change your window to be a minimum of -2 for the X variable, the maximum of +2, and then the scale, make it count by ones, then it looks normal. It looks nearly normal. So yeah, you can do that on your calculator, and just to make sure that all these conditions are good. So then if you go back and run that test one more time, so the line regression t-test, so we can do this do section, we've got a t distribution with degrees of freedom 10 because there were 12 months, so it's n minus 2, so 12 minus 2 is 10. The slope values, we're assuming it's 0, but our observed slope, which you get by running this test, it tells you the slope is -0.078, and then it even tells you what that is standardized. So the t value, which I guess I didn't label here, let me label it. That's fine, we'll use blue. So the t value is -3.097. So TCDF, or 2 times TCDF, since it's two-tail, from -infinity to -3.097, degrees of freedom 10, let me use a laser pointer, is this p-value, 0.011. And forget this, or I'll come back to that later. And forget this comment too, that's later. So based on that p-value, with all conditions met, we can conclude with a p-value of 0.011 that we reject the null hypothesis, meaning we have enough evidence to suggest there is an association. In other words, this means slope. Let me write the word slope here. That's the way you should think about it. We say association, but really we're just talking about the slope between temperature and crawling age. So that's all you would need to do. I just came up with this extra part just because it'd be useful to talk about since we're here. But I just noticed that this p-value is 0.011. That's pretty low, but keep in mind if our alpha level was 0.01 instead of 0.05, we would fail to reject, barely. And so I wanted to show you what that means in terms of a confidence interval. If you go to your calculator right now and do line regression t-interval, not t-test, but it will create a confidence interval for you super fast. And so if you make a 95% confidence interval with L1 and L2, you'll get the same thing I have here. So the slope is between -0.134 and -0.022. Both are negative. 0 is not contained in the interval, so it makes sense that we would reject the null hypothesis with this conclusion. But if we had widened that confidence interval to a 99% confidence interval, then we wouldn't reject. We'd actually fail to reject, because if we had lowered our alpha level to 0.01, because this is bigger than 0.01, and with this confidence interval you have a negative value and a positive value, so 0 would be contained in this interval. So then it would make sense that you would fail to reject the null hypothesis. So I just wanted to point that out. Fun fact, maybe it'll show up on a future test. Maybe it'll be on the AP test. So just wanted to point that out for fun. So yeah, give me some feedback if this video went better. It was much shorter, so that's nice. But if you liked the laser pointer with the pencil scanned copy, just let me know. Hopefully you're all able to collect the data in the 47-minute class period today. All right. Yeah, I will talk to you later.